Hello physics, welcome to another flipped lecture. Here we are talking about magnetism, chapter 21. There's some information in this chapter and in the next chapter that I'm going to edit for you, and we're going to bypass a couple of things because I don't think that it's something that you're going to take with you forever into your life. So this is chapter 21 edited a little bit, and chapter 22 will be as well. But we're doing the entire chapter in 1 week and in one lecture, so let's jump into it here. Magnetism. This slide you know. You know everything here except maybe the definition of the unit of a Tesla. But the magnetism was discovered very early on, and historically you're aware that initially people thought it was magic of some kind. There was all kinds of superstition about it regarding your health and what it did to have a magnet in your home and all those kinds of things. The first scientific discovery and description of them had to do with naturally occurring rocks called lodestones. And a lodestone is a rock that has a magnetic property in the way that the molecules are arranged. And they started discovering that there are two poles to these lodestones, to these naturally occurring magnets. And some very famous experiments that you read about, but I will not test you on, just for your private benefit. Now you know about them. Law of magnetic poles. This is something that you already know and are familiar with, that opposites attract and likes repel. So if you have two north poles, they repel each other, a north and a south attract each other. And so that is the law of magnetic poles. You're familiar with that. Magnets are always dipoles. You cannot get a magnet to only be a north pole. If you take a magnet and break it in half, so that what used to be the north pole is on one piece and what used to be the south pole is on the other piece, both halves of the magnet now have a north and south pole. Magnets are always, always, always dipoles, all the way down to one molecule if you were to get that small. It is the dipole nature of a molecule that, when all of these molecules are arranged in the right order, creates a dipole for the entire thing. Okay, so magnetic fields are like electrical fields, but unlike electrical fields, they have to always be dipoles. Magnetic fields are drawn similarly to electric fields with arrows coming out of the source of the magnetic charge and looping back to the opposite pole of the magnet. So magnetic fields and electrical fields look very similar when they're drawn, and they have arrows that we use, just like we use in electrical fields. The arrows in a magnetic field always point from north to south. So they leave the north pole and they go to the south pole. So depending on where the arrows are going, you can determine if you're looking at the north or the south pole of that magnet. Okay, magnetic fields are measured in Teslas. That is the unit of measurement. And a Tesla is defined as a volt times a second divided by square meters. That's the unit, and so they put all this nasty unit together that comes out of the math to calculate a magnetic field, and they called it a Tesla. And the Tesla is a massive, massive unit. If you have a 1 Tesla magnet, you have a magnet that can rip out your jewelry, remove your dental fillings, these kinds of things. So very powerful magnet if it's 1 Tesla. Most of the time the magnets that you encounter are thousandths or millionths of a Tesla. Okay, so we will not encounter a 1 Tesla magnet, and you probably will never encounter a 1 Tesla magnet in the normal course of your life, unless you decide to go into physics and study magnetism. This, just as an example of a very strong magnet, this little itsy-bitsy thing that this guy is holding is lifting up a 10-pound weight. Magnets can be very strong, but even this magnet is probably a thousandth of a Tesla. Okay, Teslas are huge units of measurement. Magnetism is measured. We talk about the magnetism of a particular material with this strange term called the relative magnetic permeability. And what we mean is, if you compare a magnetic field outside of this material to the magnetic field within the material, does the material magnify or decrease the strength of the magnetic field? Okay, so this term, this is mu, this is the lowercase Greek letter m. Okay, mu looks like a U with a tail on the front of it. Mu sub r is the relative magnetic permeability, and that is, how does this thing mess with magnetic fields? And what we do when we calculate this, it's just a ratio, and there are no units for it. Mu over mu sub naught, or mu sub 0. And what we're comparing here is the magnetic field inside the material with the magnetic field in a vacuum, or the magnetic field outside the material, ignoring the atmosphere. And so what's the magnetic field like inside divided by what it's like outside, and then that gives you a ratio, mu sub r. If something has a mu sub r much greater than 1, and when we say much, we mean like 2, so something like that, then, or something close to 2, then we would say that it is magnifying the magnetic field. It's a ferromagnetic material. It's increasing the magnetic field inside that material. So that material is resonating with the magnetic field, creating its own magnetic field in response to the magnetic field that it's exposed to. Okay, ferromagnetic materials have numbers for mu sub r that are close to 2. All right, but if it's only very, very slightly, sorry about that, very slightly above 1, like 1.03 or 1.2 or something like that, then we're talking about a material that has a relative permeability just slightly greater than 1, and it's not strongly attracted to magnetic materials. It tolerates a magnetic field. It might simulate a little bit more of a magnetic field inside it, but not very much. You're not going to get a huge number out of there. And so a paramagnetic material kind of ignores a magnetic field, is mildly stimulated by a magnetic field. And then the opposite of that would be a diamagnetic material, which has a relative permeability less than 1, which means it's actually diffusing the magnetic field. The magnetic field is less inside that material. Something like plastic would be a diamagnetic, where it is something that would be buried inside this material, does not experience the magnetic field that is outside the material, or experiences it less. Alrighty? So ferromagnetics multiply the magnetic field. Paramagnetics sort of increase it, but mostly ignore it. And then diamagnetics actually decrease the magnetic field. Alrighty? So here is an example for us to look at. If the field strength inside a material is 0.5 teslas, which would be a massive field, so this is a very, very strong magnetic field, and the field around the object placed in a vacuum is 0.3 teslas. So I want to know what's the value of mu sub r, and what kind of material is this. So it has magnified the field, right? Inside the object, it's half a Tesla. In a vacuum around the object, it's a third of a Tesla, 0.3 of a Tesla. Okay, so mu r equals mu divided by mu sub 0. This is the strength of the field in a vacuum. This is the strength of the field inside the object. This is the ratio between the two. Inside, outside. 0.5 divided by 0.3, 0.167, or 16666, etc. You have two significant digits here, 2, 2, 2. 1.7 is the answer. It is significantly bigger than 1. You're never going to have numbers that are more than like 2. I think 2 is probably the absolute maximum that you get. So 1.7 is a pretty darn big number. So this material is ferromagnetic. It is not just slightly more than 1. It is quite a bit more than 1. And so this is probably a piece of iron or something like that that is increasing the strength of the magnetic field because of its presence. Natural magnets are said to be ferromagnetic. So, oh dear. Wow, I'm having fun. Ferromagnetic, that's what I meant to do. Ferromagnetic is a category. Ferromagnetic means a magnet you find in nature. What a difference an eye makes, okay? Ferromagnetic objects are magnetic because there are regions of the rock, regions of the piece of metal, where all of the moments of magnetism, magnetic moments, are all pointing in the same direction. So that region, called a domain, has a magnetic field. And in a natural magnet, not all the domains, not all the little regions will all be pointing in the same area, but the average of all the vectors will create the overall magnetic field for the rock. So depending on how you break the rock up, you would have different domains present in the fragments, and the direction of the magnetic field may change. But a region of the rock that has all the moments of magnetism pointing in the same direction, we call it a domain. And then the average of all the domains in a naturally occurring rock gives you the magnetic field for that object. Okay, and you have that already in physical science, so that is not new to you. All the domains average out to a net magnetic field for the rock as a whole. So the Earth is a really big rock, and its core imparts a magnetic field to the Earth. Its core is mostly iron, and its core has the domains pointed together in a direction, and it is a huge magnet. The magnetic north pole, when you hold your compass, it's the north part of the needle that points north, which should make you go, but wait a minute, I thought opposites attract. Yes, they do. And so the north needle, indicating which direction north is actually pointing to the magnetic south pole of the Earth, which means up there, Canada, Greenland, Siberia, that's magnetically south. But it is geographically north, and we identify that as where the north part of the compass points, not where the north end of our magnet is. A little bit confusing. And also, to make it even a little bit more confusing, is that the magnetic North Pole does not coincide with the geographic North Pole. So where the needle points is not truly the northern point of our globe as far as the Earth's rotational axis goes. So the magnetic axis and the rotational axis are off by a little bit. Not so much that you can't use a compass, but enough that if you're being very precise, you'll see some differences. Okay? Something else that you should know, and this is an opportunity to worship God because of science, so we always want to take those. The magnetosphere. The magnetosphere is the magnetic field of the Earth and the region of space that magnetic field influences, which is actually very large. And so we cast a large magnetic shadow into the solar system, and high energy particles from the sun come blasting out of the sun, and if they could stream straight from the sun down to you, you would get cancer and die very quickly. Life would be very hard to maintain on a planet exposed to cosmic rays. But our magnetic field forces away those high energy particles and makes the Earth a much safer place to live. And we'll get into the why here in just a moment with the way the charged particles interact with magnetic fields. But they're pushed away by the magnetic field of the Earth. Two consequences of that is the fact that the Earth tends to be, well, first of all, has life on it, is shielded from the solar wind. And secondly, we get these cool things called the auroras. Around the North and the South Pole, there are bright lights in the sky, and we in Hawaii don't live anywhere near north or south enough to see those. But if you were to journey up to Alaska or down to Australia or something like that, you might run into these northern and southern lights. And what that is all the high energy cosmic particles that were deflected by the Earth's magnetic field, if they hit the Earth's field just right, actually get drawn into the poles. So again, not a lot of life on the poles, but life on the poles is a lot more irradiated than life away from the poles. And when those high energy particles come into the atmosphere glows because of the high energy radiation coming into it. And that glowing atmosphere is called the northern lights. So they're beautiful to see, but if you are seeing them a lot, then you're getting nuked. So go visit, but don't live there. Okay. This is just a picture of what I was talking about. So the high energy cosmic radiation leaving the sun, most of it is deflected away by our magnetosphere, our magnetic influence. But if it strikes it just right, it kind of gets funneled in here and it hits the poles of the planet. Those of us living in the tropics, we don't have to worry about this. People living right near the poles would definitely need to worry about this. Okay? So, magnetism has a right-hand rule. Aren't we excited? Raise your right hand if you're excited. I'm excited. Are you excited? My right hand. Okay. Electromagnetic field forces. The force of a magnetic field on a moving charge is perpendicular to both the direction of the force, the direction of the charge as motion, and the force vector of the magnetic field. And it looks like this. So your right-hand rule for electromagnetism with regard to electrons moving down a wire, and then the direction of the magnetic field. You can see already that they're arranged at a right angle. For the influence of a charged particle in a magnetic field, we need another finger. I need another finger. Okay, and you do something like this, where your thumb and your pointer finger make a 90-degree angle, and then your middle finger makes a 90-degree angle to both of them. Okay, so that's the shape. And what we do is we use the pointer finger to point to the current, the direction that the particle is moving, the charged particle. And then the magnetic field, we make this finger, and they are always at right angles to each other. And we arrange these two things to say, yes, the particle is going this way. So I'm sorry, I just said they're always right angles to each other. That's not true. They could be like this, or they could be like this. But we're going to say that they are for a moment, that they're always right angles to each other. So we're going to point the way the particle's going. We're going to stick the middle finger the direction that the magnetic field is pointing, and then we extend our thumb up. And that is the way that the charged particle moving through a magnetic field wants to go. So his forward momentum vector will be affected by this force, which means he's going to turn, right? And that is what causes charged particles from the sun, which are beaming towards us, when they are exposed to a magnetic field, right, makes them go away. And that is what causes our Earth to be shielded from those high energy charged particles. It's pretty cool. So we have a right-hand rule for the force on a charged particle in a magnetic field. Now, the direction of the charged particle is relative to the field. So if the particle is sitting still and the field is moving, then you have to point that vector in the direction that is relative motion. Which way does the particle think it's going because of the motion of the field? So it's the relative motion vector. If the field is stationary and the particle is moving, that's easier. But if they're both moving, or one is moving, the opposite is moving, then you have to do a little bit of head scratching. But we won't make you do that in this level of physics course, okay? So right-hand rule for charged particles. Now, that comes into play with, force vectors, and we get to do a little bit of math here and experience figuring out which direction is the force vector going and what is the strength or the magnitude of that vector. There's a cool little equation here. F mag equals the absolute value of Q times V times B times the sine of theta. What are all of those things? Well, the force of the magnitude, the magnitude of the force of that the particle feels with your thumb, the way that it's trying to go, is equal to the charge of the particle, and it could be positive or a negative charge, and so we need to say absolute value there. The absolute value of the charged particle times its velocity, so how fast is it moving, meters per second, okay, times the strength of the magnetic field, which is beta, boy, I'm doing a great job today. Beta is the strength of the magnetic field, times sine theta, which is the smallest angle between the lines of force of the magnetic field and the velocity of the charge. So you have to measure how far apart are the vectors for the particle's direction and the field direction. If they're 90 degrees, then sine theta, with theta being 90, is 1, and that whole term drops out. But if there's a smaller angle there, then we need to take into account that you're not getting the full force of the magnetic field on that particle. You're just getting some fraction of it. Okay, so we'll do an example with a similar equation, not with this one, but this equation is for the magnitude of force on a charged particle in a field. Okay, the same relationship exists between a charge that's in a wire and magnetic field that's brought by. So you have an electrical current going through the wire, and you bring a magnet near it, and the electrons in that wire want to leave. They get pushed by the magnetic field, and same sort of equation. The equation looks very similar. Force of the the magnitude of the push on the electrons by the magnetic field is equal to the current in the wire, that's measured in amps, times the length of the wire experiencing the magnetic field. I used a cursive L there just so that it doesn't look like little line, capital I, and lowercase l. It doesn't have to be a cursive L, but keep in mind this is an I and this is an L. Beta, again, the strength of the magnetic field, and then sine theta, same thing. What's the angle between the direction that the electrons are moving and the field lines of the magnetic field? So I is a current in the wire measured in amps. L is the length of the wire measured in meters. The longer the wire and the greater the current, the more push that it feels. So wires in a field want to move. If you were to have a wire in a magnetic field with no current running through it, the wire would just be hanging there. And then if you all of a sudden pulsed some electricity through it, the wire would move because it would experience the force of the magnetic field pushing on the electrons in that wire. Okay, so let's do a little bit of math. What is the force on a 4-meter long piece of wire carrying 5 amps of current in a magnetic field with the strength of 0.002 Tesla if the wire is running a 90-degree angle to the field lines? Okay, so here I have a 4 meters, pretty good long wire, 5 amps, pretty decent current, but I've got an average magnetic field strength. And the wire's running at 90 degrees. So here we go. Force, the magnitude of the force is current times length of wire times the magnetic field times sine theta. 5 amps, 4 meters, 0.002 Tesla, sine of 90. Sine of 90 is 1, so I can ignore that from now on. 5 times 4 is 20 times 0.002 is 0.04 newtons. Pretty straight up math. Okay, so the wire wants to move up with a force of 4 newtons, right? The current is going this way, the field is going this way, the particle wants to go this way. So the wire will actually rise in the magnetic field with a force of 0.04 newtons. Not very much, right? It's a small acceleration, but it's an average magnet. Now, what do we learn from this? The longer the current, the more wire, the stronger the force. So that's why a generator tends to have a very long wire, lots of wire, and either lots of magnets or or very big magnets. You want a lot of magnetic field strength, and you want a lot of copper wire. That's what allows generators and motors to actually do something significant here. Okay, lots of wire and strong magnets. This is a motor or a generator, depends on what you do with it. Same piece of equipment. That's kind of a smallish one. You might see this in a car as an alternator to generate electricity for the car, or maybe this is a medium-sized DC motor that might power like a pulley or something like that. But this is a much larger generator, and you can see huge magnets, miles and miles of copper wire. And when you put this much copper wire and this large of magnets together, all of a sudden you have significant forces and you can generate a lot of electricity. Okay, so there you go. If you have any questions, post them in the comments below. Have a great day. God bless you. See you tomorrow.